this is John from Optics for Hire, and I'm here again with Sergey Sidorovich, experienced optical engineer from Optics for Hire. And today we're going to talk about some of the work that he did simulating an eyepiece. Sergey, welcome. Nice to see you again.
Thank you, John. It's nice to see you too.
If you're interested in optical engineering content, please like and subscribe. And don't forget to comment below. We always appreciate hearing from you, and it helps the algorithm. Thanks. So this system, you're starting with kind of a system, very basic concept layout. And as I recall, this is something that you might use in, a head-mounted display or some kind of eyepiece system that you would, put in a visor or helmet or something like that. Tell us a little more about the device that you were trying to design for our customer.
The customer already had this device and he asked us to improve the eyepiece because he used only a single lens as an eyepiece and it works not very good. There are several reasons for this, and client wanted to achieve higher resolution, so he wanted to see more details that LCD screen shows.
Okay. And so this was your initial lab. This is what they had when they started the project. And you made some evaluation on different key parameters.
To speak in the same language with the client, I need to understand what he means when he asks to change something, and he need to understand what I'm trying to explain or what characteristics of the system I'm trying to show him.
So I see parameters I'm familiar with, the distortion, the resolution and contrast. Can you explain this idea of the actual field of view versus the apparent field of view?
These are two sides of the eyepiece. The eyepiece is for the imaging of some object in its object plane, let's say in this way. In our case, this is an LCD, and eyepiece should connect LCD size and angle of rays that falls to the human or user eye. When we're looking somewhere, we move our eyes from left, right, up, down to see different objects, and eyepiece should form beams which will fall to the eye in some angle, and the wider angle the bigger image we can see. And when we speak about the field of view of the eyepiece, from left side we have field of view of eyepiece that see the LCD screen, so eyepiece allows to see some part of the screen, and this part will be imaged for the user through these tilt beams or angled beams. And from the right side we have another field of view for the user, and this field of view for the user is defined by angles, because to see we form parallel beams if we want to user to see objects at infinite distance, or we make these beams not parallel to place virtual object at some distance in front of the user, and this distance is virtual, and size of this image that we place on some distance depends on the angle of beams that falls to the human or user eye.
Okay, so it's a difference between the real image and the virtual image, is that?
Yeah, actual field of view is actual size of the LCD screen in this case that seen through the eyepiece, and apparent field of view is the angle of user side. So this is the angle, this is the optical axis, and this is an angle of the human side. So we can look up, down, and the wider angle, the bigger image, virtual image of the LCD screen the user will see.
Okay, and so is the apparent field of view generally larger than the actual, or other way around?
Interesting question. Actual field of view is measured in millimeters, and apparent field of view we measure it in this case in degrees, and we cannot compare them directly, but we can try to compare if we will recalculate size and placement of the virtual image, and probably we can compare, and in this case I can say exactly is this bigger or not. We need to calculate this.
All right, so I probably should have come to this slide, so this would have helped you explain it a little bit, but the actual field of view of the lens is looking at the LCD, which is 28 millimeters, and this is the apparent field of view that the user's eye creates. Is that right?
Right.
Okay. So this, I should have shown this earlier. And this lens, this is what the customer is using. You simulate it to have distortion of 26%.
Yeah, you're correct. On the right side, you can see a graph of this distortion.
Okay. And so your goal is to do something better.
High resolution and better, yeah.
So here we are looking at the actual resolution of the current system, and it's quite high in the center of the field of view, but it falls rather quickly, I guess, as you get to 5 millimeters or 10 millimeters at the edge.
Yeah.
And is this symmetrical, or is it slightly?
It's symmetrical. It's symmetrical.
All right. So one of the concepts, this one concept 2, I think you had multiple concepts. We're not going to go over all of them. Is and this is not a real lens, as I understand. This is sort of an ideal lens. Is that right? This is, or is this a real lens?
Yeah, this is
virtual optical model of the lens.
Okay. All right. So in this one, distortion is 14%, which, as I remember, that's almost half of the other one. Apparent field of view is 57 on the old one and 28 on this one. So same apparent field of view and same actual field of view, but less distortion.
High resolution, high quality.
Okay. And then in terms of resolution, that was concept 2 we were looking at. Current optics is this one, so we've got much higher in the center and higher throughout. So a big improvement, maybe 50% more in most places. Maybe, 50, I'd say in most places it's about 50% better resolution, concept 2 versus their current system. And that was what you looked at was most promising. So you did look at 3 different systems. They had just different trade-offs. One was the separate lens. A 2-lens system was better. So there were sort of 3. Concept 2 was the doublet. That was what we looked at. Concept 1 was a single lens, and concept 3 was 2 lens elements. Was that surprising to you that concept 2 was the winner, or is that intuitive that a doublet would be better than 2 lenses and okay?
Not really, not. I expected that concept 2 or concept 3 will better than the separate lens. And in this case, in accordance with simulating, in accordance with design that we made, the main issue for this design was chromatical aberrations. And 2 separate lenses cannot correct chromatical aberrations better than the doublet lens. And because of we corrected chromatic aberrations, we achieved better resolution for this eyepiece. In this case, we was limited by the construction, by the sizes and number of elements that we can use in this design.
Because there's a lot of other trade-offs: how much it weighs, how big it is. Yeah.
2 more lenses here, and resolution will be good over the LCD, not in the center only.
But then that's going to add cost.
Cost, size.
A lot of other variables. Okay. Well, thanks again for showing us how you did this analysis in ZMAX Sergey. It's interesting. I appreciate your explaining again some of the work of Optical Engineers. And thank you for your time, and we'll see you on the next episode.
Thank you, John.
Thank you, Sergey. Goodbye.
Goodbye.